Hello, welcome to Pakibi TV. We will take a closer look at some of the details of the content of The Elements. The Elements is a book that systematizes Euclidean geometry. In other words, its title is The Elements. Let's look at its content. The Elements of Geometry is a book completed about 2,300 years ago, assuming we are in the year 2000. Its content is Euclidean geometry. Its birth is one of the most important events in the history of mathematics, the reasons for which are explained in more detail in this video. However, when you actually read its content, it doesn't seem very novel, and it's hard to feel why it's so extraordinary. Now let's explain those parts. The following content will consist of savoring the content of The Elements in various ways, because we're savoring it, not just explaining the main points in a straightforward manner, so the explanation might be a bit lengthy. When examining the content of The Elements to understand its mathematical meaning, you have to divide it into two parts. What immediately catches the eye are the detailed steps of logically proving the theorems of geometry. For example, the proof that the sum of the internal angles of a triangle is 180 degrees appears in the middle. Most of the content in the book is spent on proving these mathematical knowledge one by one. From a learning perspective, when studying this part, it feels like solving a puzzle, figuring out how the pieces fit together to prove what you want. The other part is the conditions at the starting point of these mathematical deductions. And from the standpoint of understanding mathematics itself, not the engineering application of mathematics, it is important to appreciate and understand this content. So let's take a look at this content. When you open The Elements, it starts with the definitions of concepts. Unlike modern books, it starts directly with the content of geometry, without any preface by the author. Of course, in a book published these days, there would be editorial notes attached at the beginning. In other words, originally it goes straight into the main topic. Let's look at the first part of the main argument, the definitions. What you'll notice in these contents is that they've defined all the objects that will appear in geometry. They have defined a total of 23 concepts. However, the way they've laid these out is not widely used in modern mathematics. There are quite novel and creative expressions like, a point is that which has no part. This could seem paradoxical, and in a sense, it's poetic. But it's not mathematical. It should be able to connect with other statements to lead to new mathematical content in a literal sense, but it can't. In modern mathematics, the basic concepts that serve as the starting point for mathematics are not redefined. They are simply left undefined. They are considered undefined concepts. Here, the conception that mathematics is the study of patterns is established. The second part is about postulates. These 5 postulates are famous, especially the 5th postulate, which became the starting point for non-Euclidean geometry and attracted the attention of many mathematicians. As explained in previous videos, the content of these postulates seems to be, firstly, so accurate that it's hard to deny. Secondly, they are factual content about mathematics or geometry, not something else. Thirdly, despite this, in modern mathematics, they become not just true, but assumed to be true. In other words, they are arbitrary. Isn't it astonishing? The fact that these mathematical truths, which seem irrefutable no matter how you look at them, ultimately boil down to just assumed to be so. The third part is about axioms. This is closer to the philosophical part than the mathematical one. Specifically, it corresponds to the rules of thought rather than the content of mathematics. For instance, let's consider the principle that if you subtract the same thing from the same thing, the results are the same. This is the fundamental principle when making x equal sign 5 minus 3 from x plus 3 equals 5, that is, moving plus 3 on the left side to minus 3 on the right side. From x plus 3 equals 5, if we subtract 3 from both sides, it remains the same. And from there, it becomes x plus 3 minus 3 equals sine x. On the other hand, the principle that the whole is larger than the part breaks down when set theory appears, and we start calculating the size of the infinite. Another point to consider is that we need to find all these seemingly obvious rules of inference with a minimum number of rules. To understand why this is significant, let's think about it. When we reason with shapes, what rules do we think by? Almost no students ask this kind of question, and historically not many scholars have asked such questions. Euclidean geometry asks this question, and a sort of answer comes out in the axioms. How many principles do you think we use? 2? 3? It doesn't seem like it would be just that few, because when we reason geometrically with shapes, we don't really feel like we're repeating the same thought over and over, like 1 plus 1 equals 2, 2 plus 1 equals 3, 3 plus 1 equals 4. So, 10? 20? The axioms of Euclidean geometry consolidate this into 5. It's not so much that it is correct to have 5, but rather the point is that they sought to find the minimum set of rules. From a modern perspective, if we say something like, when the same operation is performed on the same thing, the results are the same, numbers 2 and 3 could be integrated. By the same operation here, we can define it to include adding the same thing, subtracting the same thing, multiplying by the same thing, dividing by the same thing, and even oddly transforming it in any way. In this way, we can see that Euclid's axioms do not include multiplication or division. Why is that? Because Euclid was thinking about visible shapes, multiplication or division would appear as addition or subtraction. For instance, tripling would look like adding twice the size. Number 4 defines what it means for things to be the same. This is also a geometrical definition. Let's summarize the entire content and compare it with the structure of modern mathematics. The content of definitions is literary. This has been developed into undefined terms in modern mathematics. In simple terms, it wasn't until modern times that we discovered that the meaning of words is not mathematically significant. Postulates are referred to as axioms in modern mathematics. Their content is composed of propositions that contain unique mathematical content. Axioms transform into rules of inference in modern mathematics. These rules are reduced to one syllogism. Then what about all those contents of axioms in Euclidean geometry? They are made into axioms of mathematics and moved up. Thus, modern mathematics mainly distinguishes between pure logic and mathematics, and also collects the changes in mathematical patterns to make them more visible. Speaking about the relationship between axioms and rules, you can turn all axioms into rules and put them in, but most rules can also be transformed into axioms and put in. However, you cannot make all rules into axioms. By simplifying the rules which are commonly held by all fields of mathematics, the difference in mathematical content appears as a difference in axioms, and therefore each field of modern mathematics is determined simply by defining its axioms. As we read a bit of the elements, the contents of Euclidean geometry, we examine the significance of its detailed content and how it connects to modern mathematics. If this video was helpful, please hit the like button and subscribe. Thank you.